that's a really cool thing to watch. That basically directly link what you learn in this class into what's going on inside these things, right? And how do your phone add and subtract, connect to other things, and gets amplified and stuff like that. And what is a vacuum tube, right? That he's just talked about. All right, so let's go back to what we're talking about. Oops, I'm recording. Okay, so this last section that we're going to cover is the thin lenses, right? Last Thursday, I kind of started this section where, right, there are two different types of lenses. Well, there's more than two, but the two we're going to deal with is called, one of them is called converging lens. Hopefully the naming makes sense, where converging lens makes the rays converge. Diverging lenses, right, makes the rays diverge. But then what you can do is backtrace it, so it actually does converge in your imaginary backtracing back to a single point. Okay, and these lenses tend to be just made of two spheres. Okay, and the distance from the lens to where, let's say, the convergence for a converging lens happens is what's called a focal length. Okay, you can do the same thing with the diverging lens, where the diverging lens, they would never actually, the real rays would actually never converge in a single point. That's why it's called a diverging lens. But if you do this backtracing, you will also end up at this single point. This is also the focal length of a diverging lens, right? Okay. So there's a couple of rules dealing with these rays. Okay. In fact, I'm going to have a ruler out. Actually, I can use this one. Okay. Where, right, if a ray passes straight through the center of a lens, it doesn't get bent at all. There's actually a slight shift, as we saw from the example from last week, where let's say you have a laser beam going through a piece of glass. It does get shifted, but in this case, these lenses are so short, they're so thin, not short, so thin, we can just assume that that bending is very minimal, and you don't need to take that into account. Okay, and this is the reason why we call this the thin lens approximation. Okay, so for converging lens, right, there is some special rays that can come in. So let's say you have some parallel rays coming in like this, right? All of these rays will come in and hit a single point, right? But let's say you have a source that is a single point as opposed to parallel. Remember the two types of rays we're going to be dealing with, right? Is these parallel ones and a point source, right? When you have a point source, what happens is that it actually hits the lens and makes parallel rays for you. Okay, and that's why actually, if you ever seen, what are those things called? The ones that pirates use? What? Telescopes. Periscopes. Not telescopes. Yeah, I guess they're telescope, but they're not monoculars, right? Whatever the pirate uses, right? There tend to be two lenses on each side, right? And that's because, right, the first lens is actually to parallelize the beam, and then the other one is actually to focus it, so it actually focus on one point. Okay, so let's just do an example of how we can actually draw these ray diagrams for a converging lens. So hop up my little ruler here. Well, the first thing you want to do is draw the optical axis, right? That optical axis, you always want it to be kind of nice and solid. Okay, and that's just a horizontal line. Okay, so then what you do is you place the lens somewhere. Okay, and this somewhere depends on what we're trying to draw. Okay, in this case, I'm just going to kind of draw in the middle. Okay, right, and since it's a converging lens, it'll just kind of look like this little I don't know, leaf shape. Okay, let's say we have an object. Remember, objects are things that we're going to be putting in front or behind the lens. Let's say this object is located, somewhere over here. Okay, it could be some Christmas tree or something like that. But what we tend to use is just basically pretend it's just an arrow, right? That's straight up. Okay. All right. So what we want to do, right, when we trying to figure out what image is going to form on the other side, is we're going to do this ray tracing exercise. I'm going to do that in green. Okay. So remember, one of the first things I told you is that, well, if the ray goes through the center of the lens, it doesn't get bent, right? So the first ray we can actually draw is actually a boring run, where this is just along this line here, okay? From the bottom here, going straight through the lens, right, it's just not going to bend, right? In fact, I'm going to erase this just so you don't have to erase yours. I just want to make it so it's a little bit more balanced, top and bottom, okay? There's actually another ray that goes through straight through the center of the lens. Well, that's actually infinite of them, but there's another one that's interesting, is the ray that comes from the top of here, right, straight to the middle here, right? That one we can also figure out which direction it's going to be moving, right? So I line this up, right? Do this. Oops, didn't mean to make it blue. I want to make the rays green. Okay. Now we're going to try to, maybe we're starting to figure out what type of image is going to form on the other side, right? It seems like the top of this now becomes the bottom, right? So another way that's going to be useful is that there's going to be, you can draw some parallel ones, right? Right. If a ray goes through parallel through a lens, where should it go? Okay. I didn't mark this. I'm sorry? To the focal point, yeah. So I didn't define where the focal point is in this case, right? So let's say the focal length is like this long, right? This is F, okay? And by the way, right, this distance here is S, right? Okay? Where the image will form is actually S prime, right? The prime is the image, right? Okay? So if I draw this through a focal point, right, from where the lens is, right, right, it's going to be a little bit of finagling here. Oops, don't move. That's where the ruler is useful. 32. Okay. Okay. If I do this, okay, notice that this ray and this ray is going to meet at a single point. Okay. Both of those rays came from the top of my Christmas tree, right? So both of those rays are actually the top of the Christmas tree being formed here. Okay. So the image that's actually formed, let's do that in purple, right? It's actually going to be down here, upside down on the other side. Okay? Right. And this distance over here, let's do that in pencil purple, right? This is S prime. Right? That's the distance from my image. So this ray that's going along the straight line, that's easy to draw, right? And these two rays, those three combined together, they're known as the principal rays, okay? So these are the principal rays because they're the most useful ones, right? Right? That allows you to figure out where the top of this Christmas tree image will form, and it technically also tells you where the bottom one is formed, right? But you know the bottom is going to be along the optical axis. Okay, this little axis here is known as the optical axis. Okay, I want to know all the words. Okay, all right. Just to note down a couple more pieces of information here, right? Let's say your Christmas tree has some height h, right? The image that it forms, right, will use the height h dash, right? Right, h, sorry, h. What is that called? I'm sorry? H prime, yeah, h prime. I don't know why I forgot that. Okay, all right. So, in fact, you can relate all of this information together. The book tries to have you guys do it, and you know, with like rulers and stuff at first, but then, right? But then they basically tell you what this equation is. This is known as the thin lens equation, where it basically allows you to relate S prime, and the focal length to each other. Okay. There's actually another equation we had previously where we were just magnifying things, right? So remember this thing called magnification, right? It's just going to be h prime over h, right, with a negative sign, okay? And this happens just by using similar triangles. You can prove that this is also equal to S prime over S, right? So the combination of these two equations allows you to solve for a lot of different thin lens problem. Okay, so I'm going to show you guys a example of that. Okay, so the first example is going to be magnifying some image. Okay, so let's say we have some 4 centimeter tall flower, and it is 200 centimeters away from, you know, some lens that has the focal length of 50 centimeters. Okay, they want to ask you how far should the light detector be placed behind the lens recorder in order for the image to be well focused, and what is the diameter of the image that's going to be formed. So the setup of the problem is actually your ray tracing diagram. Okay, so I'm going to do this freehand just to save a little bit of time, so we may not be as accurate. Okay, so in this case, I'm going to place the lens kind of to the left, because we know that, well, the image has to form pretty far away, right? Okay, so I'm going to put this kind of to the left, right? And then we're going to put a little flower here that's going to be kind of short. Okay. Okay. So a little flower is going to be, right, this is where the flower is located. Okay. 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 And, oops. Sorry. I think I did the opposite of what I was supposed to do. I want the lens far away from the image. I could have done this backward, but, right, because the flower is actually far away, so I think I messed up that problem. Okay, so this flower is 4 centimeter tall, h equals 4.0 centimeter. And notice I'm leaving a lot of this stuff in centimeters. I'm not going to convert to meters because all of this stuff is going to be done in centimeters anyway. Okay, and then this distance, right, this is s, right? S is going to be equal to 200 centimeters. Okay, and this lens has a focal length about 1/4 of that. So I'm going to mark the focal length around here. Okay, okay, so this is f, and f is going to be 50 centimeter. Okay, and they're asking you where should I place the detector so that it actually makes a well-focused image. So what we do is we do our lens tracing once again, right? The boring one is down here, right? And we'll have another one that's going to be coming across like this, straight through the center of the lens. And then we do another one across here. But then this one, since it's parallel, is going to cross the focal point instead, if I can hit it. Yeah. Okay. Okay. So this is where the image is going to form, right? Okay. Right. And you can see, while from the picture, it looks like it's a little bit beyond the focal length, so we'll see is actually accurate, okay? So to actually solve this problem, right, we need our thin lens formula, which is 1 over s plus 1 over s prime equals to 1 over f, right? It's kind of similar to like capacitors in parallel and series and stuff like that, right? So the location of this s prime is what we're interested in, right? Because red, right? This is s prime, right? Okay, so we're actually trying to solve for s prime here. Okay, so if you want to solve for s prime, you go over here, and then 1 over s prime is going to be 1 over f minus 1 over s, right? You plug in 50 and 200 in here, and this is where I spend time doing calculator stuff. Okay, the focal length was 50 minus 1 over 200, which is s, right? And you want the reciprocal of that, right? So therefore, s prime is actually being mean to me because it's giving me the exact number, 3 over 200. It's actually, is that right? Sorry, 200 divided by 3. Okay, it's actually 67 centimeter. Hopefully it's 2 sig figs, yeah. Okay, so that's where you would, s prime will be 67 centimeter. So notice that from this drawing, if you draw it kind of accurately, right, you already can check whether or not this answer makes sense, right? Because this is 50 centimeters from the lens, right? And this is about 67, right? So hopefully that makes sense, okay? This is why if you actually have a ruler, it's actually very useful to draw these ray tracing diagram accurately. That way, you know when you plug in your answer, right, your formula, you know if it's right or not, okay? So, so during the final, maybe I'll just bring a bunch of rulers around so you guys can use it, okay? All right, so I'm gonna spend maybe 5 minutes to just describe what happens with a diverging lens, how you deal with that. So I'm gonna skip down to here, okay? For a diverging lens, it's very similar to converging lens, except that you're gonna have to do all this back tracing, right? Because for a diverging lens, these rays actually never meet each other. So you actually have to back trace to figure out where the focal length is, okay? So what you can do is use this to create a demagnifying glass, okay? So let's do this quick example real quick before we jump into the worksheet, where, so a diverging lens has a focal length of 50 centimeters again, is placed 100 centimeters in front of a flower. Where is the image gonna form, and what is the magnification? Okay, so once again, I'm gonna draw my optical axis, right? And then my flowers is in front of here. It actually doesn't even tell you what the height is, right? Okay, and we have a diverging lens that's going to be kind of far away from it. Okay, the way you draw a diverging lens is you just make these inverted circles. Okay, and then we just do the trace of the rays. The first ray is always the boring one, just goes along the line. The second one, right, goes into, right, the center of the lens once again, okay, and it does not get turned, right, so it actually does still pass through the bottom here, okay. The last one, which is the one that's going to go parallel, right, and the ray's going to go this way, but since it doesn't converge anywhere, what we need to do is actually place it with this back tracing thing back to the focal length, which is here, okay, okay. And the crossing between this back tracing and this ray that goes straight through the middle is where the image is going to form, okay? And this is actually a virtual image, okay? Okay. Notice that, right? If we try to figure out where the image is on the right-hand side, we have no idea what's going to meet, right? These three lines never meet each other, right? But if you did this back tracing, right, this purple line, this green line actually meet at one spot, okay? The image is actually not here. The image is actually in front of here, but much tinier, okay? So that's why it's called virtual image, okay? And that's how you do the back tracing with these diverging lenses, okay? And I think I'm gonna give you guys more time to work on the worksheet as opposed to me just plugging in formulas, right? So once you have all of this drawing done, right, you know where S is, right? S is this 100 centimeter, okay? The focal length is 50 centimeters, right? You can use this to figure out where the image is gonna form, right? This S prime, okay, is where the image is gonna form. It's actually gonna come out negative, right? Because it's a virtual image. Because it's actually really on this side, but it gives you a negative number as the answer where it forms. Sorry, bad drawing, right? S prime is the distance from the lens to the image, okay? I think I drew it towards the focal length, okay? Okay, and the magnification you can calculate by just figuring out what S prime over S is, okay? And usually when you calculate the magnification, you don't take the sign into account, okay? It's gonna come out negative, but just say that, you know, whatever it is, just put a positive, okay? In this case, it's gonna be less than 1 because it's actually a demagnifying glass. So do you mind passing these guys out and then figuring out how we can get this done in about 20 minutes?